Hello, my name is Jiafeng Zhou, and it's my Spring 2019 EE591 project presentation about maximizing abdomen tissue contrast under different B0. My personal goals of this project are to explore a bunch of theories about magnetic resonance imaging and learn how to use software and artificial data to simulate real-world situations. Moreover, I can train my coding abilities through this project. The aim of this project is to examine how to maximize image contrast for neighboring abdomen tissues under a range of B0. Several sequences such as saturation recovery, fast spin echo, and steady-state free precession will be applied to simulate how magnetization changes. The project can be divided into two parts. First is to let B0 be fixed and find best parameters that can achieve largest contrast. Second is to keep the best settings and change B0 from 3 Tesla to 0.55 Tesla to visually show how the contrast changes. The motivation of this project is that parameter choices are important to the reconstruction result. Different choices of TE, TR, and so on can largely impact the illuminance and contrast. From the image here, it can be seen that for thin sliced image, different parameter settings can make the image brighter or darker, and enhance or suppress contrast between tissues. Since tissues have different T1 and T2 values, and signal intensity is a function of T1, T2, TE, TR, and so on, adjusting TE and TR can manipulate contrast between two tissues. It will be pathologically useful because those such as liver tumors have a larger T1 than normal tissues. Moreover, abdomen tissues are all close to each other. It will be useful if contrast between two neighboring tissues is maximized, so that one tissue can be distinguishable from others. If there is a way to maximize contrast between abdomen tissues, it will be better for doctors to do examination. With the help of MATLAB, it can simulate different kinds of sequences and calculate steady-state magnetization. We can numerically simulate the process and reconstruct the image. Here is the flowchart showing the implementation process. Assume B0 is a fixed value. First process is data acquisition. T1 and T2 data should be obtained for targeting tissues. T2 is stable to B0 variation, but T1 is related to B0, so that for every B0 value, corresponding T1 should be calculated. In order to numerically find best parameters that can maximize contrast, a mesh grid is generated for TE and TR. The range for TE is 1 to 100 milliseconds, and 1 for TR is 1 to 10,000 milliseconds. Therefore, there will be TE and TR pairs, and signal intensity is calculated for each pair. Those pairs which TR is less than TE are omitted. Second process is parameter computation. Block simulation helps calculate corresponding steady-state signal intensity for every TE-TR pair. Then for each pair, contrast and contrast efficiency can be derived. Iterates through contrast array, and the indexes for maximum can be found, which is the best parameter setting. At last, read digital phantom and do some pre-process such as keeping targeting tissues and blocking all other tissues. Use block simulation again, this time apply best parameters, and the image that maximizes contrast can be constructed. Here are some figures showing the details of the process. To calculate T1 under P0, from a paper written by Portemley, it follows a simple polynomial relation. For fat, liver, muscle, and kidney, their relation between T1 and B0 are plotted in the first figure. A saturation recovery sequence is shown in the second figure, and if we generate a mesh grid of TE and TR, contrast of the grid can be shown. Yellow region indicates a higher contrast, and dark blue region indicates a lower contrast. An example of phantom mask data and reconstructed image is shown in the end. Here are the formulas for calculating steady-state signal for saturation recovery. At last, contrast is calculated by the difference of two magnetizations. For T2 weighting images, since it tends to find longest TR, contrast efficiency is maximized instead of contrast. Efficiency is calculated by dividing contrast by square root of TR. Here are the results. First, kidney and fat are examined. On the left are axial and coronal images of kidney and fat. Leftmost two images are phantom mask data. For kidney and fat, they have a large difference in T1, so T1 weighting is expected. SSFP is used for simulation. Second image shows an image with maximized contrast using best parameters when B0 is 0.55 Tesla. TE is found to be 2 milliseconds. TR is found to be 285 milliseconds. Third image is generated by TE equals to 100 milliseconds and TR equals to 1000 milliseconds. It is clear that the best parameters result in a larger contrast than the reference image. The grade of contrast efficiency also shows that there is a maximum when TE and TR is small. When B0 changes from 0.55 Tesla to 3 Tesla, contrast also increases. The last two animations show the changes of images using best parameters when B0 changes from 3 Tesla to 0.55 Tesla. Image becomes darker when B0 becomes smaller, but two tissues are still distinguishable with an acceptable contrast. Second, kidney and liver are examined. They have a similar T1 and largely different T2. For T2 weighting image, TR is long and fast spin echo is used here, since it can get more data for each excitation. Here, the echo train length is 2. It's also clear that the one with maximized contrast is much visually better than the reference image. For maximized contrast, TE equals to 48 milliseconds and TR is 2700 milliseconds. Reference image uses TE equals to 100 and TR equals to 1000 milliseconds. Contrast efficiency gets maximum when TR and TE are long. The last one is for muscle and fat. Spin echo is used here. They both differ a lot by T1 and T2. Maximum of contrast efficiency is achieved when TE is 15 milliseconds and TR is 414 milliseconds. In a word, maximum contrast can be found numerically, and for T2 weighting images, fast spin echo is good for reducing readout time. When B0 is smaller, contrast also decreases, but if parameters are optimized, two tissues are still visually distinguishable. From this project, several challenges are met. Gradient spoiled sequence was tried, but it's too computationally intensive if assumption is that gradient spoiler has 4-pi twist across the voxel. Therefore, numerical method gets long running time if algorithm has too many nested loops. Second challenge is that although there is a relation between T1 and B0, standard deviation is large. There is about 22% standard deviation, which can result in a large error range. For T2 value, standard deviation can also reach 20 milliseconds, which is about 25%. Therefore, whether simulated results are same as reality is still a question. Learning from this project, I got some experience for simulating different kinds of sequences, and get to know that although things might be trivial in the first sight, implementation can be very time-consuming during the process. Here are the references, and thanks for listening to my presentation.